Okay, so I've been working on this project called Herculus, and it's basically, you can think of it as a way to work on relational data, and it has a spreadsheet-like user interface. And the most interesting part is that you have this typed language like Haskell that you can use to transform your data. And I'm going to quickly explain like the basic concept, how it works, and then we're going to look at one example. So if you have a Herculus project, it consists of a list of tables, and every table has a bunch of columns like A, B, C, and you can either enter data into a column, or a column can depend on other columns, like this column C depends on A and B via this formula, which is in this case very simple, it's just A plus B. And like there are two interesting things to note about it. The first one is that the formulas are statically typed, so this only works if columns A and B also are of type integer. And also the formula defines this implicit dependency computation graph. So if I update 1, then also the 4 changes, which is just like in Excel. Now we can make this slightly more interesting, like this. So here we have 2 tables, a list of invoices and a list of items that can be part of the invoice. And we have this column items, which is kind of represents what I get if I join those 2 tables on the condition that the date of an item has to be within the month and the clients have to match. And in Herculus, we can very easily express this as you would expect if you are familiar with a language like Haskell, because you just filter over the list of rows in this items table. So you write filter, then you have this predicate, and you filter over the list of items, which is this table. And the predicate is just a function from, like, given a row of this table to Boolean. And in this case, it says, like, the date has to be within the month and the client has to match. So this is basically the whole concept. And what makes it interesting is that you, like, this column has type list row of the items table, but it can be any user-defined ADT. And also, like, you have all the freedom you can imagine within the formulas. So you can define arbitrary stuff. And for the rest of the talk, I'm going to show you how this, like, an example of an application that you can build with this. So this is going to be live. So in this example, is this too small? So this example is about people who trade contracts for difference, and you don't need to worry about what this is. Basically, they are betting on financial instruments, how they perform, and then you have sales agent who recruited the traders, and we want to know how much commission they make based on the trades. So in this project, you have 4 tables: the trades, the traders, the sales agents, and the commission. And this, like, the trades table is very simple. So every trade has the properties you would expect it to have, like the date where the trade closed, the position closed, the trader, the asset class that was traded, the volume of the trade, and the profit or loss that was made. And the small font says what type the column has. And this column is interesting because it's a foreign key on the traders table. So every cell is a row from the traders table. So let's look at this one. A trader has a name and itself has a foreign key on the sales agent table. So the type is a row from the sales agent table. And every sales agent has also a name. And a contract. And the contract is interesting because it defines how the commission is calculated. In this case, I modeled the contract as a list of commission schemes. And commission scheme is interesting because it's a user-defined ADT. So if I go to the definitions for this project, I can see that I defined this commission scheme ADT. So a commission scheme can either be agents can earn commission based on the volume that was traded with a given factor. So I can say, in this sales agent earns commission based on the volume with a factor of 0.1, but only for stocks. So I have this asset class type here. Or they can participate in the profit or loss of the trader. And then here I have defined this function, which is available in the whole project, which basically says for a given commission scheme and a list of trades, how much commission does the agent get. And it's very straightforward. It's just taking the list of trades and then filtering over it and mapping, filtering the list of trades and then mapping over it and summing the result. So the final table is where commission is computed. And besides this, this code, we haven't written any code so far. So now we get to the part where the logic happens. So we compute the commission for a given period from start to end and for a given sales agent. And the first thing we do is we find out which are the trades that were in the given period and where the trader that traded this trade has this sales agent as his agent. So this is similar as on the slide that I showed. Then the next thing we do is we for the list of trades that we just computed, we run the commission scheme for every scheme that's part of the contract of the sales agent. So we take the sales agent and go over the list of schemes and just run the schemes over the trades. And then we get this nice list of records where you can see, okay, for the profit and loss scheme, where the agent gets 0.2 of the, participates with a factor of 0.2, the commission was 7, and so on. And then the last thing I do is I sum over this list, basically. So I take the commission by scheme column, map over it, and take the commission, and then sum the result. And then I'm done. So basically the whole code that I need to write for this application is some definitions for the whole project, defining data types and this function, and then a few lines of code for every one of these last 3 columns. Okay, so the last thing I want to mention is the future of the project. So I have plans to make it open source, and as soon as I find time for it, I will do it. And then people are welcome to contribute. And there are lots of low-hanging fruits at the moment. So, for example, the formula language will make it very easy to migrate column types. So if I change my column from integer to string, let's say, then I can provide the show function and say, okay, migrate all the data in the column according to this function, and everything will be type checked. And you can be sure that the data will end up in the right place. Then, interfaces to external data sources will be very handy. For example, I would like to be able to import the list of trades from some external source. Then undo redo. Data validation is interesting. So for a given table, I can define a function which takes a row and goes to bool, and then I can see which of the entries are valid or not, and which not, and collaboration, and so But there are also still some conceptual challenges, like for example, this will get very slow if you have lots of data and the computation is expensive. And I need to think about what to do in this case. Like at the moment, if you change the data, everything is pushed through the computation graph. But maybe it makes more sense in certain cases to compute things on demand. Like if you want to view a cell, then it starts computing what the content of the cell looks like. Or maybe you just compute it in regular intervals or whatever. And the next thing, like there's some cases where it's very cumbersome to, like for certain applications that you want to write, it's very unintuitive how you would enter the data, so that you, yes, sometimes, yeah, okay. So, yeah, that's basically it. I think we can answer maybe one or two questions.
No, I think we're going to have to move on to the next talk, but if you're around, okay, we can take questions offline. Thank you.
All right.